So now that we know that we can work in polar form and we know how to get in and out of polar form, we need to be able to multiply and divide in polar form. And there's two very handy rules that are in your books, and shows you that if this is one complex number and this is the other complex number, if you want to multiply your complex numbers, you just multiply their modulus and add their angles. This is very handy to understand when we go to the Argand diagram and look at what happens on the Argand diagram when we multiply, a complex number by I, or a complex number by a whole number, or a complex number by another complex number. This can be a very handy and helpful rule. Similarly, if I want to divide two complex numbers, okay, Z1 over Z2, it'll be the modulus of Z1 divided by the modulus of Z2, and you subtract their angles. That could be a handy rule for multiplying in polar form, so that way you don't have to come out of polar form to multiply. If we look at this, then we have this number here. Z, I want to put to the power of 10. That means I have 1 plus I to the power of 10, which is 1 plus I times 1 plus I times 1 plus I times 1 plus I, and so on until I multiply it by itself 10 times, which is way too time consuming. It's not that I can't do it, it's just it would take too long. So in this situation, I would put it into polar form. And I'll explain why when we see how we can use De Moivre's theorem. So there's 1 plus 1i. I need its distance from the origin, which I use trigonometry for. I have the modulus is, let's call it x squared, then because it's Pythagoras theorem about to use, plus 1 squared plus 1 squared means that x squared is 2, so x is root 2. So the modulus of this is root 2. The argument, I'm going to use tan of the angle, is 1 over 1. That means the angle is 45 degrees, or pi over 4. Now, we can using this information, put it into polar form. So it's root 2 times the cos of pi over 4 plus I sine pi over 4. This is it in polar form. And I'm going to put this, that's z, I need to put z to the power of 10. Using my rules of indices, if I have two things to the same power, I can separate that out. That's root 2 to the power of 10 times the cos of pi over 4 plus I sine pi over 4 to the power of 10. Root 2 to the power of 10 is 32. And the cos of pi over 4 plus I sine pi over 4 to the power of 10, I can now apply De Moivre's theorem. And looking at that in your books, what De Moivre's theorem says is that if you're in polar form and you want to put it to any power, well, we've done this using our indices rules, but here I can bring the power down in front of the angle for the cos theta plus I sine theta, which if I use that over here, I have the cos of 10 times pi over 4 plus I sine 10 times pi over 4. That's 32 times, and you can put this into your calculator. Make sure your calculator is in radians when you do put it in, and you'll end up with the cos of 10 pi over 4, which is 0, plus I times the sine of 10 pi over 4, which is 1, times I, and then multiplying this out, I end up with 0 plus 32i. And I can plot that on my Argand diagram if I wanted to. So if I have a complex number and I want to put it to a high power, I mean, if I wanted to multiply it by itself 3 times, I may not put it into polar form, but maybe anything higher than 3, and I'd want to put it into polar form because it's too time consuming to multiply it out by itself 10 times. The reason I put it into polar form is because it's easy to deal with the power using de Moivre's theorem here by bringing the power down in front of the angle. If we look at a different question and how we might use polar form to help answer maybe a question perhaps like W is this complex number, and if I have Z to the power 4 is W, solve for Z. Now don't get confused here just because they're using Z. If I asked you x to the power 4 is equal to something, you would get the fourth root of both sides so that you could get x. That could also be to the power of a quarter because the fourth root is to the power of a quarter. And you would expect 4 solutions. So over here, just because we're using Z, it doesn't make any difference. I can get the fourth root of both sides. And I'm going to expect at the end 4 different solutions. Z equals, Z equals, Z equals, Z equals. So they cancel off and I end up with Z is equal to W. Now, the fourth root is the same as W to the power of a quarter. Why is that helpful? Well, if I could write this in polar form, I could put it to the power of a quarter and use de Moivre's theorem to figure it out. Now, this would be a situation where I would use general polar form, not just polar form. So if you plot this in your Argand diagram, a little sketch for yourself, and then put it into polar form, you would get that the modulus is 4 and the the argument is minus 2 pi over 3. We're going to put it into general polar form. And I'm going to put, this is W now, I'm going to put it to the power of a quarter. So 4 times, now if I want to put it to the power of a quarter, that's 4 to the power of a quarter, using my rules of indices, times the cos of a quarter, times I'm bringing the power down in front. And I'm choosing to put in a 0 for n in the first situation. And when I throw that into my calculator, I would end up with root 6 over 2 minus root 2 over 2i. And that's one solution. When I chose that n was 0. When I chose that, if I choose that n is 1, that's 4 to the power of a quarter times the cos of a quarter minus 2 pi over 3 plus 2 pi times n is 1 this time, plus I sine minus 2/3 over 3, sorry, quarter times the minus 2/3 plus 2 pi times 1. And if you throw all that into your calculator, you would end up with root 2 over 2 plus root 6 over 2 times I, and that would be another solution for Z. And I would keep going because I'm expecting 4 solutions. So I'd throw in n is equal to 2, and when I do that, I'd get minus root 6 over 2 plus root 2 over 2 I. And if I put in n is equal to 3, I'd end up with minus root 2 over 2 minus root 6 over 2 I. And if I put in n is equal to 4, I'd just go back to the first solution here because there are only 4 solutions.